Okay, so let's go ahead and get started. We got a bunch of material to cover today. I'm going to finish up nomenclature, starting with alcohols and then amines. Amines actually won't take very long because they're similar to alcohols. The difference between what we're going to do today and what we were doing in the previous lecture is that we're going to be dealing with actual functional groups taking priority in the nomenclature. So before we had alkanes, which were being named as alkanes, and then we were modifying those alkane chains with substituents. What we're going to do now is we're going to identify an alcohol by name. So instead of something being something-ane, because it's going to contain a hydroxyl group making it an alcohol, we're going to call it something-something-all. So what that looks like is, whereas this would be methane, if we get rid of one of these hydrogens and add a hydroxyl group, the presence of the hydroxyl group makes this an alcohol, which we'll have this named meth instead of ane, methanol. So another example. Where we would normally have ethane, because we have an ethane hydroxyl group, this is now ethane instead of the E, also ethanol. And that's the difference between a functional group and a substituent, because now we're going to be naming the base, the parent chain for that functionality. So a lot of the process is identical in terms of the rules, so it should be very familiar to what we were doing last class. First thing you do is identify the parent chain, but in this case the parent chain is going to be the longest continuous chain which contains the functional group. So a little modifier. And then the second rule is we're going to number the parent chain so that the functional group, in this case, the hydroxyl, has the lowest number possible. So what's this look like? That's a little fast. Let's do this again. So in this case, our longest chain, simple to identify. We have our 4 carbons in what would be butane, but because it contains an alcohol or hydroxyl group, we're going to name it as an alcohol. So we're going to number from this side so that the number for the functional group is as low as possible. So this is one of the tricks. Alcohols and amines have, I learned under one nomenclature style, and they've since modified it to reduce ambiguity, but they still accept the old style, so there's actually 2 acceptable ways to name alcohols. So I would have called this 2-butanol. It's also acceptable to call this butan-2-ol. As the compounds get more complicated, this actually makes it a little easier to show where the alcohol groups are, or the hydroxyl groups are on the compound. Because I did it this way for so long, default to this. And then everything else in front of that is identical. There's no modification. So as we add substituents and modify these, make them more complex, everything out in front for the modification stays the same. And the only difference is how we address this. So there are multiple correct answers for naming alcohols. Let's do another one. I did something wrong with my example. Instead of making that up, I'm going to move on. That is not a good example. That is a bad example. What happens if we have multiple alcohols? So in the case of having multiple hydroxyl groups, let's just modify this. In this case, because we have a pair of hydroxyls, we will name this as a diol. So instead of, with the case of substituents where we say something something dimethyl, this will be something something diol. And we're going to number so that the hydroxyl groups have the lowest total value. So in this case, we would number from this side 1, 2, 3, 4, 5, 6. So that 2 plus 4 is 6. If we numbered from the other direction, it would be 3 plus 5 would be 8. So because we're going this direction, we'll have the lowest possible value. And so this would be either 2, 4 hexanol, or it would be hexan 2, 4. Oh, no, it's not. Diol 2, 4 diol. And I can see as I do this more over time the value of putting the 2, 4 next to the diol because it tells you exactly where. It gives you the numbers right next to the functional groups. So both are fine. I don't have a strong preference for the way you do it. Both ways are good. Practice both ways. Not a bad way to go. So, yeah. Because it would be hexanol, not hexal. So that N stays on. The only thing that falls off is the E at the end. So let's see here. Thing that throws people occasionally is that functional groups get prioritization in the numbering scheme over substituents. So let's say we have 2, 3, 4 here, hydroxyl here. People are tempted because they're not necessarily separating what a functional group is versus a substituent. So they'll see this chain and they'll go, okay, we're going to number from the nearest substituent 1, 2, 3, 4. That would be a mistake because the functional group has nomenclature priority. So because of that, this is 1, 2, 3, 4. So this is going to be a 4 chloro 2 1, 2, 3, 4. Actually, which way? You guys hit me with the 2 variations of this.
4 chloro.
Or
Chloro. Butane.
Yeah. Exactly. So you just have to keep in mind when you're seeing these things, there is the functional group will get priority over the substituent. Yeah.
So if this is the new system that they've done, does that mean for like the final that they put out, that's the system they're going to be writing it in?
I'm not quite sure.
I mean, it doesn't matter either way, but
Either's acceptable. They're both correct. And then the last point is that you still are going to list the substituents in alphabetical order, even though the all is going to go on the end. So we're always going to put the hydroxyl group designated as an alcohol on the end of the name to identify it as an alcohol when we read it. And then all of the substituents will be out in front, just like on alkanes listed in alphabetical order, regardless of their number. So let's see, let's do one of those. So now we have an alkyl group, a halogen, and a hydroxyl group. These are both substituents. That's a functional group. So we're going to number from the side with the functional group for the longest chain. So we're going to have an octanol, and that'll give us a 4-ethyl and a 7-bromo. Which one comes first alphabetically? Bromo. So this will be 7-bromo, 4-ethyl. What's the rest of it? We got 2-octanol or octan 2-ol. Either is okay. Okay, so that's the turbo version, but you can see that this is really, really similar in terms of the way we approach the nomenclature to what we were doing in the last class. It's just that we're not naming them as alkanes, we're naming them as alcohols. Other than that, there's only some tiny variations on the theme. So the more, I was talking to somebody after class, doing this is like reading the rules to Magic the Gathering. I'm glad somebody thought that was funny. Without playing the game. I mean, like, I have no idea what is going on right now. But until you get in, when you start to play the game, a couple hands, you're like, oh, I'm a nerd. I mean, no, yeah, that too. Yeah. I'm figuring it out, and then there's clarifications along the way, and people make little tweaks, and you see scenarios where you get kind of nuance to the rules. The only way to really do nomenclature, you're not going to really understand nomenclature until you're running problems. You have to get in and just run problems. And I opened up already, I'm ahead of the game this time, all of the problems are available to you after you finish the homework. So just jump in, run problems, have the rules next to you, check in on the rule if you miss on the practices. And the more nomenclature you do, the more automatic it'll become, and you won't have to be referencing these series of rules for very long. If you're trying to learn the rules steadfast before you take on the homework problems, that's a really challenging way to approach it. Yeah?
Is there a dash after
Yes, there would be. However, there wouldn't be a dash between the ethyl and the octan.
Oh, so it would be 4-ethyl octan.
4-ethyl octan 2-ol.
Oh,
Yeah.
yes, okay.
So amines, very similar to alcohols. In terms of nomenclature. And we also have some common names for amines. For instance, this is methylamine. This is ethylamine. So the small amines are really, you basically name the simple alkane. If it has an easy note, and just say amine, everyone's like, oh, okay. They're going to know exactly what you're talking about. So it's when we get a little bit larger. And in this case, as we substitute this functional group and name it as an amine instead of an alkane, we're going to take the E off of the alkane and substitute amine. So that's not too hard to remember. And we could do this pretty much exactly like with alcohols. 1, 2, 3, 4, 5. We would number from the side closest to the functional group, which has the longest, that includes the longest chain, which includes the functional group. In this case, 1, 2, 3, 4, 5. So this would be 1 pentamine. Or just like alcohols, you can call it pentan 1-amine. Either is correct. The funkiness happens if we get into multiple bonds to the amino nitrogen. Because what do you name it? What do you number it as? There's no number ascribed to the nitrogen. So what we do is we use this really creative way. Instead of numbering it, we put an N in there to say that we have things bound to it. So let's take a look at that. Let's say we've got this. The longest chain that contains the functional group is going to be the longest continuous carbon chain, which contains the functional group. Because this nitrogen's in the middle of what you would see as the chain stops here. This is considered an alkyl modifier to this chain. So what's our longest chain? It's going to be from this carbon to this carbon. And we're going to number it from the side closest to the functional group. That's what PhDs let you do. Sometimes you just get to skip 3s. But not today. You do purge all the unnecessary low priority things like how to count. That's super real. So in this case, we're going to have 2 substituents. We've got the 3-chloro group and we've got an N-methyl group. So this would be 3-chloro N-methyl 1-butanamine, or methyl butan 1-amine. Either is okay.
Still have the N before, so it's N-methyl butanamine or N-methyl butan 1-amine.
This is telling you that the methyl group as a substituent is
But so you do still need the N then?
Yes.
Do the other way of naming it.
Absolutely.
Okay.
Yeah.
So can you clarify why the method is amine instead of like?
Because if we had it here, it would be 1-methyl.
Oh, okay. Sorry, I didn't see that the methyl was
On the nitrogen.
Okay.
Yeah.
Okay, that makes sense. Okay. Before you listen to stories.
Or never mind, sorry, that's up there. Why wouldn't you include the chloro when you write it the other way with N-methyl?
Because that's all there. I'm just
Okay.
don't want to write the whole thing again. If you have multiple things bound to the nitrogen that are identical, ooh, this is good. Where's the longest? What's the longest chain? Where does it start? Everyone try to get the answer in your head. Does it start here? Ah, couldn't fool you. What about here? Here?
Yes.
This is the longest chain that contains the functional group. The functional group happens to be modified with 2 methyl substituents, and the main chain is modified by a halogen.
It's like N-dimethyl.
This is going to be N-dimethyl. Right? So this is going to be 4-bromo, N dimethyl, because there could be another methyl over here. This could be a methyl here with 1 methyl there, and then it would be a N3-dimethyl.
Yeah, we did that.
What time is it? It's not even like.
This one back here.
We're being watched. I know. Uh-oh. Last thing about amines is that they commonly.
Methyl or dimethylamine?
Dimethyl 2-pentanamine.
Yes. Dimethyl 2-pentanamine or dimethyl pentan 2-amine. Either is correct. It's really common for amines to form, just like it's really common for ammonia to accept a proton, forming ammonium. Amino groups are very similar in that regard. So when you get 4 bonds to the nitrogen, you're going to get a positive charge. And if you have something that this is tetramethyl ammonium. So in the case that you have a positive charge on it, you label it as an ammonium versus an amine. And this is really important because these will often be paired with anions, making salts. So if we had this paired with a hydroxyl group, this would be a tetramethyl ammonium hydroxide salt. And you see this really commonly with drugs, where you'll have a charge on the nitrogen, and it's done intentionally to make them more soluble so that we can have them circulate in our bloodstream. at biological pH. So tiny modifier, if it's charged, is no longer amine, it's an ammonium. And you're almost always going to have that in salt form. So that could be a hydroxide salt, it could be a chloride salt, it could be a citrate salt, it could be any number of counter ions to it. I'm going to not lecture on non-covalent interactions. I'm going to leave that to you guys to go over in the book. It's 100% review from late 105 or early 106, depending on who you'd had it from. But it has, couple quick things just to review. Terms that you should be comfortable with. You should be able to rationalize polarity based on the net dipole. Or if you have a region of high electrical density because of lone pairs or because something's electronegative, you should be able to talk about or identify London dispersion forces, which are just induced dipole to induced dipole interactions from things being in proximity to each other. You should be able to identify full-time permanent dipole to dipole interactions. So this is induced dipole to induced dipole, which is a very weak force. These are all considered weak forces. Dipole-dipole interactions, hydrogen bonding, which is the strongest of our weak forces because it has a low percent covalent character, about 10% covalent nature. Common hydrogen bonding motifs with alcohols. This hydrogen, can hydrogen bond these two lone pairs? Can hydrogen bond to other hydrogens? Water is unique in that it can participate in 4 different hydrogen bonding events simultaneously, even though it rarely does. It can. Alcohol can only do 3 because it has the ability to donate electrons for 2 hydrogen bonds and accept electrons for a hydrogen bond. But it's 1 hydrogen short of 4. Amino groups can do the exact same thing. Except in the case of amino groups, we have 1 lone pair and a pair of hydrogens. So it can hydrogen bond from the lone pair, donating to a hydrogen bond, or it can accept electrons for a pair of hydrogen bonds. Majority of whenever you see an OH or an NH2, think about potential for hydrogen bonding. Think about how these impact physical properties such as melting points and boiling points. The more strongly they associate with themselves, the more energy it will take to excite them into gas phase or liquid phase. And think about the impacts on solubility with the most simple description is polar things dissolve polar things, and nonpolar things tend to dissolve nonpolar things. So like dissolves like. Super quick review of these. Just read the sections. They're well written, and I don't think there's a lot to be gained from me basically reading those chapters out loud. I can't elaborate in a way that I think is helpful. But what I can elaborate on what's helpful is cyclohexanes. So let's get into that. And this is something that often gives people fits because of the attention to detail in the manipulations. This, for a lot of people, is a good example of when a kit is super useful because you can just pre-build a cyclohexane, and then you can actually take it into different conformations and ring flip and put it into boat. You can do all kinds of things with a kit that may improve your ability to visualize what we're doing on the board here. So before we quite get to cyclohexanes, let's talk about rotations, about single bonds. Anytime you have a sigma bond and no pi bonds, you have some degree of free rotation there. So if we've got ethane, let me redraw that. We've got our ethane. With a little bit, the energy levels will change slightly depending on where these protons are versus the protons in three-dimensional space. But you can freely rotate this bond because this is just electrons being shared linearly between two nuclei. There's no reason, there's not like a metal rod in there that you can't twist. It's when you start to add pi bonds that you get the rigidity, because they have to be perfectly aligned p orbitals to do that. But for the single bond, it functionally has free rotation. And because of this, we can evaluate different confomers, and confomer is just another word for conformation, by sighting down any particular bond. So when we do this, we have a tool called the Newman projection. So what I'm going to do is I'm going to draw viewing from this way through this way. And what that looks like is we put a circle for our line of sight, and up front we've got our three bonds. Let me redraw that really fast because I want to draw it as shown. The lines that meet are the one in front. Behind are the lines for the bonds behind. So looking at it from this direction, we have these two hydrogens up high and angled away from each other. And looking at it planarly, like in 2 dimensions, 120 degrees, even though the bond angles are 109.5-ish. So I could call this hydrogen A, B, C. This would be hydrogen C. This would be hydrogen A. This would be hydrogen B. And then on the other side, you can see this one's up. These two are down. We can call these X, Y, Z. And so we've got X, Y, and Z. This orientation, where everything has as much space about it as possible, is called a staggered conformation. Now, if we take this first series and rotate them 60 degrees, the rear didn't change at all. Whoop. X, Z, Y. But the front did rotate, where A now rotated 60 degrees up here, B 60 degrees down here, C 60 degrees over here. And this is called an eclipse conformation. Now, these are not energetically identical. This version is slightly preferred. Why would this version be preferred over this version? Best guess based on what you know so far.
It's lower energy.
Solar energy?
It's lower.
Oh,
Yes.
But why is it more stable? Why is it lower energy?
It's further apart.
Because the bonds are further apart?
The atoms are further apart.
You guys are thinking of steric hindrance, which is a term we're going to get to in just a second. We have more room around everything. The funny thing is with protons being so small, hydrogens being so small, there isn't actually any spatial interaction between the protons even in the eclipsed position. So what this is actually an effect called, did I draw this down? Oh yes, I did. There's an effect here called hyperconjugation. What we have is an alignment of bonding orbitals with alignment of anti-bonding orbitals from the opposite side. So for all these sp3 hybrid orbitals, remember, you've got a large bonding and a small anti-bonding node. And what's happening is in the staggered conformation, this bonding orbital aligns with this anti-bonding orbital, and this bonding orbital aligns with that anti-bonding orbital. And through space, these anti-bonding orbitals actually relieve a little bit of, spread out the electrical density just a little bit, which stabilizes these positions. So it's actually alignment of orbitals in this particular case, and it happens for this one with this one and this one with this one. So you get a whole bunch of bonding orbitals aligning with a whole bunch of antibonding orbitals, which gives you hyperconjugation, which is a stabilizing effect. There isn't actually any through space interaction between the nuclei in the eclipsed conformation. Yet, as we add bulkier groups to this, that will become a very powerful effect. So steric hindrance will become an issue in just a second. So let's take a look at that example with steric hindrance being an issue. Let's look at ethane, or else butane. 1, 2. What we're going to do is sight down this middle bond like my eyeball between the 2 and 3 bond, and that means that each of these will have, instead of 3 hydrogens, we'll have a pair of hydrogens and a methyl group on each of these carbons, on the 2 and 3 carbon. So when we look at our Newman projection, we could have something that looks like this. I'm going to draw the eclipsed version first. Where the methyls are directly across from each other. Then we'll start rotating things. Oop, getting ahead of myself. Let's put them up top.
Silly question.
Yes.
Why couldn't you rotate? So when you compared the staggered and eclipsed confomers, you rotated the front set of atoms. Why couldn't you just rotate the back and hold the front steady?
You can.
Okay. You just chose to do the one.
Yeah. Just so that people knew what I was specifically intending to rotate in my drawing.
Yeah.
You can totally rotate the back.
Cool.
There's no reason you can't do that. So me just erase this so it's not bugging anybody. So this is representative of this, where the hydrogens are eclipsed and the methyls are eclipsed. And this is called eclipsed. If we rotate the front 60 degrees, so we've now got a 60-degree rotation. This is a type of staggered, but we have two different types of staggers, just like we have two different types of eclipse. Let's do another 60-degree rotation. So I'll rotate this down. It's going to get a little tight here. Notice that in this particular case, we have another eclipse, but that these eclipses have a methyl to hydrogen versus both methyls. And then if we do one last rotation, which gives us all of our possibilities here, and bring the methyl down here, what did I do? Yep, okay. Yep, nope. Good. I knew something was horribly wrong there. There we go. Okay. Whew! I was like, wow, that didn't work out the way it was planned. 60 more degrees. Here we go. So this is staggered, but there's a big difference in energy because in this position, the methyls are as far away from each other as possible. This is called an anti-position, and this is called a gauche position. If we keep rotating it, we just go back into our previous scenario so that we go eclipsed, gauche, eclipsed, anti, eclipsed, gauche, back to eclipsed for every 60-degree rotation. Now, in terms of energy level, these are not all equivalent. This is our highest energy. This is our lowest energy. These are in the middle. And what I want you guys to do is look up figure 3.7, and it'll give you a really nice oscillating curve, which will be better drawn than what I can do on the board, and it'll show you those relative energy levels. Not uncommon to be given a question where you see this energy versus position curve and are asked to locate what position is gauche, what position is anti, etc. So you probably want to pay attention to that particular figure. Yeah?
The eclipse is the highest, the one on the far left is the highest energy, and the one on the far right is
The second highest. And then gauche will be the second lowest, and anti will be the lowest. So let's move on to, we have a little bit of idea about freedom of bond rotation and Newman projections and how we look at that. Let's look at cycloalkanes. So, the four that we're interested in, cyclopropane, cyclobutane, cyclohexane, and cyclohexane, and that is 60 degrees, that's 90 degrees, that is 108 degrees, and this is 120 degrees. All these are tetrahedral bonds because each of these has two hydrogens to it, so, well, they all want to be tetrahedral. they want to be 109.5 degrees. Because for bonds, sigma bonds to share electrons linearly across the nuclei, the orbitals need to be aligned linearly. If you have kink from non-ideal angles, it's impossible to as efficiently or stably share electrons between those two nuclei sigma bonds. So, which of these four, let me just throw, that has what we call significant ring strain. This has significant ring strain. These two, which one should be more stable? Right. It's what everyone thought for a long time. However, then they started to do thermodynamic experiments and realized that this one is just as stable as this one. Why is that? It's three-dimensional. So this fooled lots of people who are really smart for a long time because they're so focused on these being planar. They're not planar. If you construct one of these out of an atom kit and twist it, you'll see how not planar it can be. We can actually twist this so that nearly all of these bonds come out to pretty darn close to 109.5 degrees. And what we're going to do is look at what that is in its most stable position and start talking about preferences within those different conformers. Okay, so conformers of cyclohexane specifically. Because there's going to be a lot of multiple choice, you're not going to be asked to do an enormous amount of drawing of cyclohexane rings, but I recommend practicing it because identifying something as ring flip is different than actually performing a ring flip. I really think that drawing these things manually helps the brain integrate the concept more than just looking at solutions and identifying solutions. Creating the solution de novo is better than just identification. So you can always identify if you can create. It doesn't go the other way around. So what this looks like three-dimensionally in its most stable conformer is what's called a chair conformation. Because it looks kind of like a garden chair. That's how it looks. And the easiest way to draw this, as you do it more and more and more, you want to have enough angle so that you can display where all the substituents are. So some people say the easiest way to draw this is to have two parallel lines with a little bit of a stagger, and then you can come in with your other lines. That's a pretty good approach until you get the hang of it. The trick is that you need to have enough room so you can draw in the two different types of bonds. There's two types of bonds we're going to be dealing with. There's going to be axial bonds and equatorial bonds. So the axial bonds are all on the vertical axis, straight up and down, relative to your structure. And the equatorial bonds are going to be parallel to the two bonds, one bond away from it. So this bond is pretty much parallel to those bonds. This bond pretty much parallel to this bond. This one's a little steep, but everyone gets the idea when they're looking at it. These are equatorial positions. Now, let's see, how do we want to draw this? These different conformers are not rigid. They're more stable than other conformers, but they can move back and forth between different chair conformers. So What I mean by that is we can, the book talks about the boat conformation, and the boat conformation, when do we talk about that? Oh, here it is. The boat is an intermediate between a ring flip. So a ring flip happens when this end of the ring moves up and this end of the ring moves down. But it doesn't happen all at once. It goes through what we call a boat. And the boat is a scenario where both are up. And these two positions are called flagpole. When they're near each other, you can see that in NMR because of their proximity. They affect one another. But as this rotates up, you go into boat. And then as part of equilibrium, it has a choice. It can either rotate back down to where it was originally, or it can stay up, and this one can get pushed down to the opposite chair. So we have an equilibrium process here, and then we have an equilibrium process going to the other chair conformation. And what that looks like is like this. I'm going to do something here. There we go. So this is one chair conformation. This is another chair conformation. This position is equatorial. This position is axial. Say, Dr. McGill, you changed your color coding. No, I didn't. The bonds that were orange are still orange. The bonds that were black are still black. What happens during a ring flip is that the equatorial and axial locations change for every bond that's on the ring. So let's look at this carbon specifically, which is this carbon to start. In the first conformer, the orange bond was in the equatorial position, and it's on the bottom. And this bond in the axial position is on the top. This one is still on the top, and this is still on the bottom. Their relative orientation of top and bottom doesn't change, but their axial versus equatorial relative to the ring does. And you can think of this as equatorial. If you were to draw this in a plane like this, the equatorial bonds are close to along the lines of the plane, whereas the axial are close to perpendicular to the plane. That's the rationale for equator, equatorial versus axis, axial. Now, if these were all hydrogens, this would be 50-50 in equilibrium. One wouldn't have preference over the other because they're functionally identical in terms of all of their through space interactions. However, let's change something up. Let's make running out of cool colors. Let's make this a methyl. As drawn with that as a methyl group, in this conformer, this chair conformer, it's on the equatorial position, and it's on the bottom of the two. When we do the ring flip, it's going to stay on the bottom. It's really common when people do ring flips. The biggest mistake people do at the gate is they'll do a ring flip with this, and it'll look like this, and they'll draw on their bonds, and everything's looking good, and they're like, okay, hydrogen, carbon, let's say carbon stays here, and everything flipping all of it, so everything's flipping around. This involves breaking bonds and reforming bonds. It's not a flip. To put the carbon up here involves taking it from this position and moving it up. So you don't want to flip out like people like, oh my God, I'm flipping out the random stuff all over the place. And they get it wrong. So don't freak out. Top one stays top. Bottom one stays bottom. Top one's top. Bottom stays bottom. The difference is that what was equatorial is now axial. What was axial is now equatorial. And the reason this matters is because of 1,3-diaxial interactions. Which are through space interactions which are non-ideal. So hydrogens are very, very small. Methyls are quite a bit bigger. I'm drawing it like this, but really it should be drawn like this. Which obviously, because of bond lengths, takes up a lot more space. So with the methyl here, we get through space interactions here and here through the other axial groups. Things on equatorial positions do not experience diaxial interactions because they're out on the periphery. So because of this, this is a slightly more strained version of this. And if we were to describe the equilibrium would favor the first because it has lower diaxial interactions than the second. The larger these groups get, methyl, the minor preference. It has a minor diaxial interaction. If we were to describe the equilibrium for this numerically with KEQ, which is going to just equal the ratio, molar equivalent of the equatorial over the axial position of the substituent. If the substituent is hydrogen, it's going to be 1-to-1, because if this is hydrogen, they're equal. If it's methyl, it's 18. So there is an 18-to-1 preference for this over that. Energetically, that's not an enormous favoritism. It doesn't take a lot of difference in energy to cause that degree of skew. But it's still significant because it's an 18-1 versus 1-to-1. If you make this an ethyl group, it becomes 21-to-1. It's not that big of a difference. What if we make a really bulky group like a T-butyl group? A tert-butyl group has a carbon with 3 methyls attached to it. That's a tert-butyl group. This has a 4,500-to-1 preference. So the bulkier the group is, the larger the substituent is, the more it's going to skew the equilibrium away from these diaxial interactions. If we make this a T-butyl group, you can see why there's some through space issues, some spatial constraints. The degree, the magnitude of these diaxial interactions are going to be significantly greater because it's such a bulky group. Therefore, this will be strongly preferred because we're putting that bulky group out off to the periphery where it's not going to have those interactions. If you have multiple bulky groups that can experience, let's do that as a separate example. Let's just do it. Yeah. Okay. I have time for one or two questions so far before I move on to the next layer. Oh no. The loquacious class is suddenly super quiet. This is not a good sign. There's seriously no questions? It's that clear? Top stays on top, bottom stays on bottom. Just flip the rings. It actually is that simple. It's just that once you leave class and you see the homework question, you're like, what was that? It's going to be okay. It'll be fine. Also, if you're asked to draw one of these and you do this, like a lightning bolt, and you're like, okay, all the vertical things are vertical, and now I've got to make things parallel, so it's going to be like this. Yup, pretty much parallel. No human can grade that. I consider that an intentional foul. The student's like, he can't grade that. I'm going to argue for at least half credit. Unsuccessfully. So yeah, don't. Also, if you don't leave yourself enough space and you do it like this, same issue. Exactly same issue. And if you do this, same issue. So, this is like Goldilocks and the Three Bears. I want it to be just right. Right? Okay, so. I know. You didn't realize there should be an art prereq to OChem. I know. Sorry, not sorry. All right, so let's talk about sidedness. When you have two groups on a cyclic system, we need to be able to talk about their relative orientation. So if I have a methyl here and a methyl here, and these are both coming up out of plane, and then the other thing's down underneath pointing away from plane, that's going to have a different chemical property than this one, where one is up out of plane and the other one is into plane. When things are on the same side of the ring, because we have this plane, when they're on the same side of the ring, either above or below, this is called cis orientation. When they're on opposite sides, this is trans orientation. It only works when you have two things to compare to. So we have a third thing, it becomes ambiguous. We'll have a different type of nomenclature for defining that. But for two, we can go cis and trans. Now, what does this look like three-dimensionally? So we've got our chair. It's going to draw in all of our bonds. That's close enough. And we'll call this carbon and this carbon we'll call this 1, we'll call this 2, 3, 4, we'll call this 1, we'll call this 4. Both of these are up on top of the ring, coming up at you. So you look at this and you're like, which one's on top? That one's on top. That one's on top. And the rest of those positions are hydrogens, because we're not identifying them as anything other than implicit hydrogens. So this is cis. If we were looking at trans, solid bar coming up out of plane, trans going away, so this one's on top, this is on the bottom of the plane. This would now be on the bottom. So we'd have one on top, one on the bottom, and this would be trans orientation. This is why that up and down tracking becomes so important, because then if we ring flip this, the top stays the top, the bottom stays the bottom. This is still the exact same compound in terms of bonds. It's still trans because one's on top, one's on bottom relative to the ring's equatorial plane. But what was equatorial is now axial, and what was axial was equatorial. So they were both drawn equatorial, and now they're both axial. Aha. Do we have any diaxial interactions with these methyls? No. Do we have any diaxial interactions between these methyls and their respective 1,3 protons? Yeah. So even though it's exactly the same compound, one of these confomers will be preferred. Which one? A or B? A will be preferred because the methyls, the bulky groups that can participate in diaxial interactions, are on the equator. Here, over there, they're not. Now, if I had drawn this with 1 on the equator and 1 on the axial, let's take a look at that scenario. When I do the ring flip, this stays on top and this stays on top. So this stays on top, and now that stays on top. We have 1 equatorial and 1 axial. This can participate in diaxial interactions. And now we have this equatorial. This axial can participate in the exact same number of diaxial interactions. So in this case, you'd have a 50-50 split. There would be no preference in these two confomers. So if you're asked to draw the most stable version, you have to get everything positioned right relative to the equatorial plane. You have to do a ring flip, and then you have to assess which one is most stable based on the axial-diaxial interactions. Yeah?
So the cis, which has 1 on the equatorial, 1 on the axial, those will be 50-50, but the trans will be preferable to the
Nope.
other way around?
Nope. Depends on where they're at. Because what if I did, it's a good question, that. So 1, 2, 3, 4. Same. Let me fix this so that it actually gets an effect. There's still This is also another really common thing. Issue. In this case, the top one is equatorial. In this case, the top one is axial. In this case, the top one is equatorial. In this case, the top one is axial. Top means on top of the plane. So if this one and this one are both on top, let's say here and here, when I ring flip, one's equatorial, one's axial, this will become axial, this will become equatorial. Because each position always flips. But if I have, and these are all trans, if this is trans to this, excuse me, cis, if this is cis to this, and I ring flip, this is equatorial and that's equatorial, they will both become axial, and you'll have one scenario where they have diaxial interactions and one where there are no diaxial interactions. So the location on the ring matters. There isn't a steadfast rule where all cis ones behave one way and all trans ones behave another way, because the way they behave will matter if it's on opposite bonds. Good question. Give me 2 minutes to draw something really fast. Fused rings. So it's really common when you're looking at pictures of drugs, because that's what everybody does for fun, is to see these ring systems of cyclohexanes that are fused together. They are not planar either. When you see fused rings, it can look like this, in which these are tetrahedral carbons. You can even look like tetrahedral carbons, and these are trans fused, which are the more stable because these bulky groups are out on the equator. And they're trans because the protons are on opposite sides of the ring. Or not my best moment in drawing. Okay, this is a cis fused. The bulky group is now axial, and one's equatorial. This can have diaxial interactions here and here. Therefore, this is going to be less stable, but they can be fused in both of these ways biologically. So there's a lot of three-dimensional texture to these multi-cyclic systems that's not evident when you just see them flat. That's all we got. That's the whole chapter. Good luck. Jump in. Start running problems. It'll become easier as you do more. Have a good weekend.